There's a galaxy out there that defies everything our eyes can see, a place that looks like a void, a silent expanse of darkness when viewed through ordinary telescopes. But switch to radio frequencies, and suddenly it screams. This cosmic enigma, where silence and sound collide, is one of the universe's most captivating puzzles. Why does something so quiet, invisible light become a roaring tempest of energy when we listen with radio ears? The answer lies in the hidden layers of reality, where the universe operates in wavelengths our eyes were never designed to perceive. This isn't just a scientific curiosity, it's a reminder of how much we still don't know about the cosmos, and how every discovery peels back another layer of mystery. Think about the quietest place you've ever been: a deep forest at night, a vast desert under the stars. Now imagine that silence isn't emptiness at all, but a curtain hiding an unimaginable storm. That's exactly what's happening in these radio-screaming galaxies. Behind the veil of darkness, supermassive black holes devour matter with such fury that they send shockwaves across the cosmos, while magnetic fields twist and warp into cosmic accelerators, launching particles at near light speed. These are the forces that turn silence into a symphony of radio waves, a language of the universe that only specialized instruments can translate. And what they're telling us is both humbling and thrilling. The universe is far stranger, far more dynamic than we ever dreamed. This journey isn't just about decoding a scientific oddity, it's about rewiring how we see the cosmos. For centuries, we relied on light to guide our understanding, but now we know the universe speaks in many voices. Some are whispers, some are shouts, and some, like the screams of these silent galaxies, force us to question everything. What else is hiding in plain sight, invisible to our eyes but blazing in other spectra? What secrets are locked in the radio waves that ripple through space, carrying stories of violence, creation, and phenomena we've yet to name? Strap in, because by the end of this exploration, you'll never look at the night sky the same way again. The cosmos is calling, and it's time to listen. The silent galaxy illusion is one of astronomy's greatest sleight of hand tricks, a cosmic magic act where emptiness is anything but. Picture a galaxy so faint in visible light that it barely registers, its stars sparse, its glow dim. To our eyes, it's a ghost, but switch to radio observations and the illusion shatters. What seemed inert suddenly crackles with energy, its invisible tendrils stretching across space, pulsing with signals louder than a supernova's aftermath. This isn't just a difference in perception, it's a fundamental mismatch between how the universe presents itself and how it truly behaves. The secret lies in the engines powering these galaxies. While optical telescopes catch the glow of stars, radio waves reveal the fingerprints of chaos, supermassive black holes spinning at their cores, swallowing gas and dust in feeding frenzies so violent they fling particles outward at nearly the speed of light. These jets, invisible to our eyes, become torrents of radio emission, painting the darkness with signatures of destruction and rebirth. Magnetic fields, twisted like cosmic tornadoes, act as natural particle accelerators, ramping up the energy until the silence erupts into a roar. But why does this duality exist at all? It all comes down to scale. Stars dominate the visible universe, but their light is just a fraction of the story. The real action happens in the shadows, where black holes, gas clouds, and magnetic fields interact in ways that don't produce much visible light but generate staggering amounts of radio waves. It's like hearing thunder but seeing no lightning. The storm is there, just operating on frequencies our eyes can't decode. This illusion forces us to rethink how galaxies live and die. What we once dismissed as quiet, aging relics might actually be powerhouses in disguise, their true nature hidden until we listen instead of look. And that's the real revelation. The universe doesn't cater to human senses. It broadcasts its dramas across every wavelength, and if we only watch the visible show, we're missing most of the performance. The silent galaxies aren't silent at all. They've been screaming all along. We just needed the right ears to hear them. Radio astronomy is like giving the universe a voice it never knew it had. While our eyes see only a sliver of reality, visible light, radio telescopes tune into the cosmic static, the hidden chatter of galaxies, black holes, and interstellar storms. Imagine standing in a pitch-black room, thinking it's empty, until someone flips on a thermal camera, and suddenly the walls are alive with heat signatures, movement, energy you couldn't perceive before. That's the power of radio astronomy. It doesn't just show us what's hidden, it rewrites the story of what we thought we knew. Take cosmic dust, for example. To optical telescopes, dense clouds of dust and gas are like curtains drawn across a stage, blocking the light of stars behind them. But radio waves slip right through, revealing nurseries where stars are born, or the chaotic orbits of gas spiraling into black holes. This isn't just a technical upgrade, it's a paradigm shift. Suddenly, regions of space that seemed barren are bustling with activity, their secrets broadcast in wavelengths our eyes can't see but our instruments can hear. Then there's the role of magnetic fields, invisible architects shaping the cosmos. Invisible light, they're ghosts, but in radio frequencies, they're impossible to ignore. Charged particles spiraling along these fields emit synchrotron radiation, a type of radio wave that paints the magnetic landscape in vivid detail. It's how we've mapped the colossal jets erupting from galaxy cores, or the delicate filaments threading through supernova remnants. These structures don't just exist, they dominate the energy budget of the universe, yet they're utterly invisible without radio eyes. And let's not forget the high-energy particles, cosmic rays accelerated to nearly light speed. When these particles collide with gas or magnetic fields, they don't glow, they scream in radio. These are the signatures of some of the most violent events in existence. Supermassive black holes shredding stars, colliding galaxy clusters, or the shockwaves of ancient stellar explosions. Optical telescopes might catch the aftermath, but radio waves show us the machinery behind the spectacle, the engines driving the chaos. This is why silent galaxies scream in radio. Their visible light might be faint, but their hidden activity, jets, shocks, particle acceleration, is deafening. It's a reminder that the universe doesn't perform for human senses. It operates on its own terms across every wavelength, and if we want to understand it, we have to listen to the full symphony, not just the melody. Radio astronomy isn't just a tool, it's a revolution in perception, proving that sometimes the most profound truths are whispered in frequencies we once thought were silent. At the core of these seemingly silent galaxies, something extraordinary is happening. A supermassive black hole, millions to billions of times heavier than our sun, is turning the void into a cosmic powerhouse. These invisible giants might not shine in visible light, but their influence is anything but subtle. Picture a whirlpool in space, so strong that not even light can escape its grip, yet so violent that it warps everything around it into a frenzy. As gas, dust, and even stars spiral toward the black hole, friction heats the material to millions of degrees, turning it into a scorching maelstrom of plasma. This isn't just heat, it's raw energy radiating outward in radio waves that pierce the darkness like a beacon. But the real spectacle happens above and below the black hole, where physics defies intuition. Magnetic fields, twisted by the black hole's spin, channel some of that doomed material into jets, twin beams of particles shot into space at nearly the speed of light. These jets aren't gentle streams, they're cosmic fire hoses blasting across thousands of light years, carving through galaxies and beyond. When they slam into intergalactic gas, they create shockwaves so massive they glow in radio frequencies, forming colossal lobes that can dwarf the galaxy itself. It's like watching a silent volcano suddenly erupt with a force that reshapes the landscape. So why do these jets exist? It all comes down to the black hole's insatiable appetite and its inability to swallow everything at once. Just as a whirlpool can't consume all the water at once, a black hole can't devour all the matter falling into it. Some of that material gets redirected, funneled along magnetic field lines and launched outward in a desperate escape attempt. The energy involved is staggering enough to outshine entire galaxies, yet invisible to our eyes. That's the irony of these silent screamers. The more violent they are, the darker they appear in visible light, their true fury only revealed when we switch to radio vision. And here's where it gets even stranger. These jets aren't just random outbursts, they're precision instruments, sculpted by forces we're still unraveling. The black hole's spin acts like a cosmic drill, winding magnetic fields into tight coils that act as particle accelerators, boosting electrons and protons to energies beyond anything we could recreate on Earth. Some theories suggest these jets might even seed the universe with the raw ingredients for future stars and galaxies, turning destruction into creation. It's a reminder that in the cosmos, even the most violent events can have consequences that ripple across eons. The next time you look up at a seemingly quiet patch of sky, remember, it might not be quiet at all. Hidden in the darkness, a supermassive black hole could be orchestrating a radio symphony, its jets writing their violent poetry across the cosmos. We're just beginning to understand the full story, but one thing is clear. The universe's most powerful voices often speak in wavelengths we're only learning to hear. These relativistic jets are nature's ultimate particle accelerators, operating on scales that dwarf anything humanity could ever build. Picture the Large Hadron Collider, our most powerful machine, capable of hurling particles at 99.99% the speed of light. Now imagine a cosmic version, fueled not by human engineering but by the gravitational fury of a supermassive black hole, a natural collider with beams so intense they could stretch from our solar system to the nearest star and back. That's the raw power packed into these jets, where electrons and protons surf magnetic shockwaves to energies millions of times greater than anything we've achieved on Earth. What's truly mind-bending is how these jets form in the first place. As matter spirals toward a black hole's event horizon, it doesn't just vanish quietly. The black hole's rotation twists space-time itself, dragging magnetic fields along like cosmic spaghetti. These fields become tightly wound springs, storing unimaginable energy until snap. They recoil, flinging charged particles outward in narrow, focused beams. It's like cracking a whip made of pure magnetism, accelerating particles so efficiently that they outpace the most violent supernova. But why do some galaxies unleash these jets while others remain quiet? The answer might lie in the black hole's diet. Active, jet-producing galaxies often have a steady supply of gas and stars falling into their cores, keeping their black holes well-fed and their magnetic fields churning. In contrast, dormant galaxies might have exhausted their fuel, their black holes sitting idle like engines without gasoline. There's also the role of galactic collisions, cosmic pile-ups that can funnel fresh material toward a black hole, suddenly awakening a dormant beast and triggering jet formation. The aftermath of these jets is just as fascinating. As they plow through intergalactic space, they don't just fade away, they leave behind colossal radio lobes, glowing remnants that can persist for hundreds of millions of years. These lobes act like cosmic billboards, advertising the black holes past outbursts long after the jets themselves have shut off. In some cases, they even heat the surrounding gas, preventing it from cooling and forming new stars, effectively putting a galactic neighborhood into stasis. Yet for all their destructive potential, these jets might also be cosmic sculptors. Some theories suggest they could distribute heavy elements forged in galactic cores across vast distances, seeding future generations of stars and planets. Others propose they might even help regulate galaxy growth, their energy acting as a thermostat for star formation. It's a paradox. The same forces that tear through space with unimaginable violence might also be key to building the universe as we know it. So the next time you hear about a quiet galaxy, remember, it might just be between outbursts. These jets are fleeting phenomena on cosmic timescales, flickering on and off over millions of years. We're catching mere snapshots of their activity, like glimpsing a thunderstorm through a keyhole. The full story of how they shape galaxies, influence cosmic evolution, and push the limits of physics is still being written, one radio wave at a time. Active galactic nuclei are like the beating hearts of galaxies gone wild, cosmic engines so powerful they can outshine every star in their host galaxy combined, yet remain nearly invisible unless we listen in radio frequencies. These AGN aren't just black holes sitting quietly in the dark. They're feasting, spinning, and unleashing energy on scales that defy imagination. At their core, a supermassive black hole gorges on gas, dust, and even unlucky stars. But here's the twist: not everything that falls in gets swallowed. Some of that material gets caught in a swirling maelstrom just outside the event horizon, forming what's called an accretion disk. Picture water circling a drain, but heated to millions of degrees, glowing with X-rays and ultraviolet light, and tangled in magnetic fields so intense they could reshape the fabric of space. Now here's where the radio screaming begins. That accretion disk isn't just a passive buffet, it's a particle accelerator. Magnetic fields threading through the disk twist and snap like rubber bands, launching high-energy electrons outward. Some get funneled into those colossal jets we talked about earlier, while others spiral along magnetic field lines, emitting radio waves as they go. This is synchrotron radiation, the same process that lights up man-made particle accelerators but on a galactic scale. The result, a galaxy that might look dim or even empty in visible light, becomes a beacon in radio frequencies, its core blazing with energy we'd never see with our eyes alone. But not all AGN are created equal. Some roar with radio emissions while others barely murmur. The difference often comes down to two things: fuel and spin. A black hole with a rich diet, say, from a recent galactic collision funneling fresh gas its way, can rev up its accretion disk to extreme levels, producing brighter and more complex radio structures. Meanwhile, the black hole's spin acts like a turbocharger. Faster rotation means tighter wound magnetic fields, which can launch more powerful jets. It's the cosmic equivalent of an engine running at full throttle versus one idling quietly. And then there's orientation, a simple but mind-bending factor. If we're looking straight down the barrel of one of those jets, the AGN might appear as a quasar, dazzling across multiple wavelengths. But if we're seeing it from the side, the jet's radio emission might dominate, while the visible light gets blocked by thick clouds of dust. This is why some AGN seem to hide in plain sight, their true nature only revealed when we switch from optical telescopes to radio antennas. But AGN don't just sit there shouting into the void. They shape their entire galaxies. The energy pouring out from these nuclei can heat surrounding gas, preventing it from cooling and forming new stars. In some cases, they might even trigger star formation by compressing gas clouds with their shock waves. It's a push and pull between creation and destruction, with the AGN acting as both architect and wrecking ball. What's truly humbling is realizing how much we're still piecing together. These cosmic powerhouses challenge our understanding of physics, energy, and even time itself. Every new radio observation peels back another layer, revealing structures more intricate than we predicted: filaments, bubbles, and loops that hint at processes we've yet to fully grasp. The universe doesn't just operate in extremes, it thrives in them, and AGN are the ultimate proof. So the next time you hear about a quiet galaxy, remember, its silence might just be a trick of the light. Switch to radio, and you might find it's been screaming all along. Not all cosmic screams come from black holes. Sometimes the universe's radio roar is a nursery song. In these silent but deafening galaxies, the chaos isn't fueled by a supermassive beast at the core, but by the birth and death of stars on a colossal scale. Picture a stellar factory where massive young stars, dozens of times heavier than our Sun, ignite in rapid succession. Their ultraviolet radiation is so intense it strips electrons from nearby gas atoms, ionizing entire clouds and lighting them up like neon signs in radio frequencies. These star-forming regions don't just glow, they crackle with energy, their radio signatures painting a portrait of creation happening at breakneck speed. But where there's star birth, star death inevitably follows. The most massive of these young stars live fast and die violently, exploding as supernova within just a few million years. These explosions don't fade quietly. They send shockwaves plowing through interstellar gas, accelerating particles to near light speeds and leaving behind radio-bright remnants that can linger for thousands of years. It's a cosmic feedback loop. Star formation lights up the radio sky, and supernova amplify it, their combined emissions turning what looks like a dormant galaxy into a radio powerhouse. So how do astronomers tell the difference between a galaxy screaming from star formation versus one shouting from black hole activity? The clues lie in the details of the radio emission. Black hole jets tend to produce highly collimated, narrow beams of radio waves, often paired with symmetrical lobes stretching far beyond the galaxy. Star-forming regions, on the other hand, create more chaotic, widespread radio signatures, bubbles, and filaments where young stars and supernova have stirred the interstellar medium like spoons in frothing milk. There's also the spectrum of the radio waves themselves. Synchrotron radiation from black hole jets tends to be louder at higher frequencies, while star-forming regions often show telltale signs of free emission, a smoother radio fingerprint caused by electrons interacting with ionized gas. Dust plays a sneaky role in this cosmic masquerade. In galaxies where star formation runs rampant, thick dust clouds can absorb nearly all the visible light, making the galaxy appear faint or even invisible to optical telescopes. But radio waves slip through effortlessly, revealing the frenzy hidden behind the curtain. This is why some of the most radio-loud galaxies look eerily quiet in visible light. Their brilliance isn't missing. It's just being broadcast on a wavelength our eyes can't see. The interplay between creation and destruction in these galaxies is more than just a curiosity, it's a window into how galaxies evolve. Rampant star formation can exhaust a galaxy's gas reserves, leaving it barren and aging. Supernova, while destructive, also seed the cosmos with heavy elements crucial for planets and life. And sometimes the line blurs entirely. Supermassive black holes and star formation can fuel each other, with black hole jets compressing gas clouds to trigger new stars, or supernova dumping material toward a galaxy's core to feed the lurking beast. What looks like a simple radio scream is really a layered story of cosmic forces in tension. The universe doesn't just hide its secrets in darkness, it encodes them in frequencies, waiting for us to tune in and listen closely. And every time we do, we uncover another piece of the puzzle: how galaxies live, die, and sometimes how they scream without making a sound. Magnetic fields are the universe's unseen puppeteers, weaving through galaxies with invisible threads that tug at everything from stray electrons to colossal gas clouds. Invisible light, they leave no trace but switch to radio frequencies, and suddenly their fingerprints are everywhere: glowing tendrils, vast loops, and intricate webs painted across the cosmos by electrons spiraling at nearly light speed. This is synchrotron radiation, the cosmic equivalent of a neon sign buzzing to life, where charged particles caught in magnetic whirlpools release energy as radio waves. The result, a galaxy that looks silent in optical light, becomes a canvas of magnetic artistry when viewed through radio eyes. These fields don't just decorate space, they shape it. Picture a galaxy's magnetic field like a network of highways for charged particles. Gas clouds moving along these invisible roads collide, compress, and sometimes collapse into new stars. Jets from supermassive black holes, instead of spraying chaotically, get funneled into tight beams by magnetic channels, carving precise paths through interstellar space. Even cosmic rays, those high-energy particles zipping through the universe, are steered by these fields, their trajectories bending like compass needles in a storm. Without magnetic fields, galaxies would lack structure, their gas and energy dissipating into chaos. But where do these cosmic magnets come from? The seeds might be as old as the universe itself. In the early cosmos, faint magnetic fields could have formed from primordial turbulence or the birth of the first stars. Over billions of years, these weak fields got stretched, twisted, and amplified by the motion of gas and the rotation of galaxies, a process called the dynamo effect, akin to how Earth's molten core generates our planet's magnetic field. Supernovae add fuel to the fire, their shockwaves turning pockets of magnetism into galaxy-spanning force fields. The result is a self-reinforcing cycle. Magnetic fields guide gas, gas motion strengthens fields, and round it goes, shaping galaxies in ways we're only beginning to map. The real magic happens in the extremes. Near black holes, magnetic fields become cosmic slingshots, launching particles to energies that defy earthly physics. In colliding galaxies, they tangle into knots, creating radio-bright shock fronts where particles accelerate to nearly light speed. Even in quiet galaxies, these fields quietly orchestrate the slow dance of gas clouds, nudging them toward star formation or drifting them into the void. It's a reminder that the universe isn't just governed by gravity. Magnetism is an invisible co-author in the story of how galaxies live, evolve, and sometimes scream. What's astonishing is how much we've learned by listening rather than looking. Optical telescopes show us the stars, but radio waves reveal the scaffolding, the magnetic architecture holding everything together. And just like a building's hidden framework determines its strength, these fields dictate a galaxy's fate. Too weak and star formation sputters, too turbulent and gas gets shredded before it can coalesce. The balance is delicate and the consequences are written in radio light. Every silent galaxy that screams in radio frequencies is sending us a message, one written in magnetic ink, waiting for us to decode. Synchrotron radiation is the universe's way of turning chaos into a radio broadcast, a spectacular light show invisible to our eyes, but blazing across the cosmos in frequencies only specialized telescopes can catch. Imagine an electron caught in a magnetic whirlpool, spiraling at nearly the speed of light. Every twist, every turn forces it to shed energy, not as heat or visible light, but as radio waves that ripple outward like ripples in a pond. This is synchrotron radiation, the signature scream of galaxies hiding in plain sight. Unlike starlight, which depends on temperature, this emission is non-thermal, born purely from motion and magnetism. That's why a galaxy can appear cold and dark in visible light while roaring in radio frequencies. Its true energy is locked in the dance of particles and fields, not in the glow of stars. What makes this phenomenon so fascinating is its sheer versatility. In galaxies with frenzied star formation, supernova shockwaves accelerate electrons into magnetic labyrinths, turning entire regions into synchrotron factories. Around supermassive black holes, jets hurl particles through magnetic fields so intense they become natural radio lighthouses. But even seemingly quiet galaxies can host this process, perhaps from ancient jets that have faded or lingering magnetic turbulence from collisions long past. The common thread: wherever charged particles meet magnetic fields in motion, synchrotron radiation follows, painting the cosmos in radio brushstrokes. Decoding these signals is like listening to a cosmic Morse code. Astronomers don't just measure the strength of the radio waves, they study their polarization, the orientation of the waves as they arrive. Polarized radio emission is a smoking gun for synchrotron radiation, revealing the hidden geometry of magnetic fields. Tightly wound spiral patterns in polarization maps hint at orderly fields, perhaps from a black hole's jet. Chaotic polarization, on the other hand, might point to turbulent star-forming regions or the aftermath of galactic collisions. It's forensic science on a galactic scale, where every ripple in the radio data tells a story about forces shaping the universe. The tools for this work are as extraordinary as the phenomena they reveal. Radio telescopes like the Very Large Array or the Atacama Large Millimeter Array don't just capture faint signals, they piece together intricate portraits of magnetic fields and particle flows. Combining these observations with data from X-ray and infrared telescopes creates a multi-wavelength fingerprint, letting astronomers distinguish synchrotron radiation from other processes. For example, if a galaxy's radio emission aligns perfectly with X-ray hotspots, it's likely powered by a black hole's jet. If it's diffuse and matches regions of ultraviolet light, star formation might be the culprit. But the real breakthrough came when scientists realized synchrotron radiation isn't just a side effect, it's a tracer of the universe's most violent and creative processes. The same mechanisms that light up radio galaxies also shape their evolution. Magnetic fields, amplified by swirling gas or black hole jets, can suppress star formation by preventing gas clouds from collapsing. Or they might channel energy into cosmic rays which seed future generations of stars. It's a reminder that the universe doesn't just operate in visible light, it thrums with hidden forces, and synchrotron radiation is one of our clearest windows into that invisible dance. So the next time you hear about a silent galaxy, remember, its radio scream isn't just noise. It's a coded message about magnetic fields, particle accelerators, and the unseen engines driving galactic life. And with every new observation, we're learning to listen more carefully, to hear not just the roar, but the whispers of physics playing out on scales we're only beginning to grasp. Radio telescopes are the ears of the cosmos, massive, intricate instruments designed to catch whispers from the void that our eyes could never see. Unlike optical telescopes that rely on visible light, these giants tune into the universe's radio symphony, picking up wavelengths that can stretch from the length of a football field to smaller than a grain of sand. Take ALMA, the Atacama Large Millimeter Array, perched high in Chile's desert where the air is thin and dry, perfect for catching faint radio signals without interference from water vapor. Or the Very Large Array in New Mexico, its 27 dish antennas arranged in a sprawling Y shape, working in unison to mimic a single telescope dozens of miles wide. Then there's China's FAST, the 500-meter aperture spherical telescope, nestled in a natural karst basin, its colossal bowl scanning the sky with unmatched sensitivity. These aren't just tools, they're time machines capturing signals that have traveled billions of years to reach us. But how do they turn static into science? It starts with a dish, a curved surface that acts like a cosmic funnel, reflecting radio waves onto a receiver. The receiver amplifies these faint signals, often billions of times weaker than a smartphone's transmission, and converts them into data. Here's where the magic of interferometry comes in. By linking multiple telescopes across vast distances, astronomers create a virtual observatory with resolution so sharp it could spot a coin on the moon. The farther apart the telescopes, the finer the details they can resolve, like a camera with a zoom lens spanning continents. This technique has let us map the magnetic fields of distant galaxies, trace the jets of supermassive black holes, and even detect the faint glow of gas from the universe's first stars. Yet for all their power, radio telescopes face challenges as immense as the cosmos itself. Earth's atmosphere is mostly transparent to radio waves, but human-made interference, cell phones, satellites, even car engines can drown out cosmic signals. That's why many radio observatories sit in remote deserts or valleys, shielded by mountains or radio-quiet regulations. Then there's the sheer volume of data. A single observation can generate petabytes of information, requiring supercomputers to process and algorithms to filter out noise. And let's not forget the weather. While optical telescopes fear clouds, radio telescopes battle wind, which can flex their delicate dish surfaces, distorting the signals they're built to capture. What's remarkable is how these obstacles have sparked innovation. To combat interference, engineers design receivers with pinpoint precision, tuning out earthly noise while amplifying cosmic whispers. To handle data, astronomers borrow techniques from machine learning, training algorithms to recognize the subtle fingerprints of distant galaxies in a sea of static. And when dishes can't be built bigger, interferometry lets them grow virtually, pushing the limits of what we can observe. Every challenge has become a stepping stone, turning radio astronomy into one of the most transformative fields in science. The next time you see an image of a galaxy's radio roar, its jets arcing across space, its magnetic fields swirling like cosmic fingerprints, remember the ingenuity behind that snapshot. It's not just a picture, it's a testament to human curiosity, a collaboration of engineers, astronomers, and mathematicians working to decode the universe's hidden language. Without these telescopes, the silent galaxies would stay silent to us, their screams lost in the noise of space. But thanks to them, we're not just observers anymore. We're listeners tuning into a broadcast that's been playing for 13 billion years. The interstellar medium is the cosmic stage where galaxies write their own futures. An invisible sea of gas and dust threading between stars, so sparse it would qualify as a vacuum on Earth, yet so vast it dictates the fate of entire galaxies. Invisible light, this medium might seem like mere background static, but tune into radio frequencies, and it transforms into a dynamic canvas of creation and destruction. Picture it as a galaxy's circulatory system. When supermassive black holes or supernova inject energy into this tenuous gas, the shock waves ripple outward, heating, compressing, or dispersing the very material that could form new stars. This isn't just physics, it's a feedback loop with consequences spanning millions of years, where the aftermath of one stellar generation determines the birth of the next. Take a galaxy like Messier 82, a so-called starburst system where stars form at a frenzied pace. To optical telescopes, it's a fireworks display of young, hot stars. But radio observations reveal the hidden cost of that frenzy. Supernova explosions churning the interstellar medium into a turbulent soup, their shockwaves carving bubbles and filaments that glow in radio light. These structures aren't just scars, they're regulators. By heating the surrounding gas, they prevent it from cooling and collapsing into new stars, effectively putting a ceiling on the galaxy's growth. It's a self-balancing act. Too much star formation leads to too many supernova, which then stifle further star formation. The galaxy, in a sense, becomes its own thermostat. But black holes add another layer to this dance. In galaxies with active nuclei, jets plowing through the interstellar medium don't just leave radio-bright trails, they sculpt entire ecosystems. Imagine a jet slamming into a gas cloud at nearly light speed. The impact can trigger shock waves that compress adjacent gas, sparking pockets of star formation like cosmic dominoes. Conversely, that same jet might blow gas clean out of the galaxy entirely, starving future stars of raw material. This push and pull between creation and destruction, feeding and famine, is written in the radio signatures of these systems. The silent galaxies that scream in radio frequencies, their interstellar medium is often caught in this very tug of war, with radio waves acting as the scorekeeper. The real surprise is how long-lasting these effects can be. Gas heated by a black hole's outburst might take hundreds of millions of years to cool back down, meaning a single violent event can echo across cosmic epochs. Some astronomers even suspect this process explains why massive galaxies today aren't as star-rich as they could be. Their central black holes, active in the past, might have unplugged their own star-forming factories eons ago. The interstellar medium remembers its radio glow, a fossil record of ancient upheavals. Yet amid all this chaos, there's delicate balance. In quieter galaxies, where supernova and black holes aren't as disruptive, the interstellar medium settles into a slower rhythm. Cool, dense gas clouds gradually collapse under gravity's pull, birthing stars at a more measured pace. Here, radio emissions might reveal not the roar of feedback but the murmur of gas slowly cycling through phases, from diffuse atoms to molecular nurseries. It's a reminder that not all galaxies are locked in tumult. Some whisper their stories in softer radio tones, their interstellar medium a cradle rather than a battleground. What makes this feedback loop so pivotal is its universality. Whether a galaxy is a starburst frenzy or a quiet backwater, the interplay between its stars, black holes, and interstellar medium shapes its destiny. And because this dance plays out in radio wavelengths, it's often invisible to traditional telescopes. That's the irony. The silent galaxies aren't silent at all. They're just speaking a language we had to learn to hear. Galactic winds are the invisible freight trains of the cosmos, vast rivers of gas streaming out of galaxies at speeds that defy comprehension, carrying energy and material into the void. Picture a hurricane, but one that spans tens of thousands of light years. Its gusts not of air but of ionized particles, dust, and magnetic fields. These winds don't howl in the traditional sense. Instead, they scream in radio frequencies, their passage marked by shock waves and turbulence that light up like cosmic neon signs. And while they might seem destructive, they're also sculptors, shaping not just their home galaxies but the entire intergalactic landscape around them. These outflows aren't gentle breezes, they're tsunamis of energy, powered by two of the universe's most violent processes. In some galaxies, it's the fury of star formation, supernova exploding in rapid succession, their combined force blowing gas outward like leaves in a storm. In others, it's the wrath of an active galactic nucleus, where a supermassive black hole's jets and radiation pressurize surrounding gas until it bursts free, a pressure valve for the galaxy's pent-up energy. The result is the same, a wind so powerful it can strip a galaxy of its star-forming fuel, leaving behind a husk that might look silent in visible light but crackles with radio noise from the aftermath. But here's where it gets even more fascinating. As these winds collide with the thin gas between galaxies, they don't just vanish, they create shock fronts that emit synchrotron radiation, the same process that lights up black hole jets. These collisions are like cosmic traffic accidents, with particles getting flung to high energies and magnetic fields twisting into intricate knots. Radio telescopes pick up these signatures, revealing the wind's paths as glowing filaments or bubbles stretching far beyond the galaxy's visible edges. It's a ghostly imprint, a reminder that even when a galaxy seems quiet, its influence can stretch across millions of light years. The impact of these winds isn't just local, it's cosmic. In galaxy clusters, where hundreds or thousands of galaxies swarm like bees, galactic winds contribute to the intracluster medium, the superheated gas filling the space between them. This gas isn't just a backdrop, it's a record of the cluster's history, enriched by heavy elements blown out by countless winds over billions of years. Some theories suggest these outflows might even regulate star formation across entire clusters, with winds from one galaxy stifling star birth in another by heating shared gas reservoirs. It's a delicate balance where the screams of one galaxy can whisper into the evolution of countless others, yet for all their power, galactic winds are also fleeting. They might rage for tens of millions of years, a blink in cosmic time before fading away. What's left behind tells a story, galaxies stripped of their gas, growing redder and quieter as star formation grinds to a halt. But even in their silence, these galaxies bear the marks of their past outbursts, radio-bright relics of winds that once roared. The universe, it seems, has a way of turning even its most violent acts into echoes, faint but enduring, waiting for us to tune in and listen. Dark matter might be invisible, but its fingerprints are all over the cosmos, especially when it comes to those silent galaxies that scream in radio frequencies. While dark matter itself doesn't emit, absorb, or reflect light, its gravitational pull shapes everything around it, bending the paths of gas, stars, and even the radio waves we detect. Imagine a hidden puppeteer, tugging at the strings of a galaxy's magnetic fields or steering particles into dense clusters where they emit synchrotron radiation. That's the subtle power of dark matter. It doesn't just lurk in the shadows, it orchestrates them. Some of the most tantalizing theories suggest dark matter might not be completely silent on the radio dial. Certain hypothetical particles, like WIMP, weakly interacting massive particles, could annihilate or decay when they collide, releasing energy that might manifest as faint radio signals. Picture two invisible particles smashing together in the depths of a galaxy, their destruction sparking a ripple of photons in radio wavelengths. These signals would be achingly faint, buried under the roar of black hole jets and supernova remnants, but they'd carry a unique signature, smooth, diffuse, and centered in regions where visible matter is scarce but gravity says something massive must lurk. The hunt for these whispers is already underway. Radio telescopes are scanning galaxies with unusually high dark matter content, dwarf galaxies, for example, where stars are few but gravitational pull is strong. Others are probing the hearts of galaxy clusters where dark matter density peaks. The challenge, distinguishing a potential dark matter signal from the cosmic background noise. It's like listening for a single violin in a symphony orchestra where every other instrument is playing at full volume. But why focus on radio? Unlike X-rays or gamma rays, which might also reveal dark matter interactions, radio waves can travel vast distances without being absorbed, carrying information from the deepest corners of the universe. They're also sensitive to low-energy processes, perfect for catching the faintest murmurs of particle decay. And if dark matter does have a radio voice, it might explain some of the unexplained excess emissions astronomers have spotted in certain galaxies' glows that don't quite match known astrophysical sources. The implications of a detection would be staggering. Not only would it confirm the existence of specific dark matter particles, but it could also reveal how they're distributed, how they interact, and even how they've shaped galaxy evolution over billions of years. Silent galaxies, once thought to be cosmic backwaters, might become Rosetta Stones for decoding dark matter's role in the universe. For now, the search remains a high-stakes game of patience and precision. Every null result narrows the possibilities, guiding theorists toward new models. And with next-generation radio telescopes like the Square Kilometre Array coming online, sensitivity will reach unprecedented levels. The cosmos is full of voices, some shouting, some whispering. Dark matters might be the quietest of all, but if we learn to listen closely, it could rewrite everything we know about the universe's hidden architecture. Galaxy mergers are the ultimate cosmic demolition derbies, violent, chaotic events where entire galaxies smash together, twisting their stars, gas, and black holes into a frenzy. To our eyes, these collisions might look like slow-motion dances, spanning hundreds of millions of years, but switch to radio frequencies, and the serene spectacle erupts into a cacophony. The same forces that render some galaxies silent, invisible light-sparse star populations, dust-shrouded cores, become the very ingredients for a radio roar when galaxies collide. It's like two quiet neighborhoods suddenly merging into a bustling metropolis, with all the chaos and energy that comes with it. At the heart of this transformation is gravity's ruthless efficiency. As galaxies spiral toward each other, their mutual pull tugs gas clouds from their orderly orbits, funneling them toward the supermassive black holes at their centers. These black holes, once starved of fuel, suddenly find themselves at an all-you-can-eat buffet. The influx of gas revs up their accretion disks to blinding temperatures, igniting active galactic nuclei that blast jets of particles across space. Meanwhile, the same gas clouds, compressed by the collision's shockwaves, ignite bursts of star formation so intense they outshine entire galaxies. The result: a fireworks display of synchrotron radiation, as newborn massive stars live fast, die young, and leave behind supernovae that further energize the surrounding magnetic fields. But the real spectacle lies in the aftermath. Radio telescopes capture the fallout in stunning detailed tidal tails of gas stretched like taffy, lobes of radio emission ballooning far beyond the galaxy's visible edges, and sometimes the telltale double nuclei of black holes spiraling toward an eventual merger of their own. These features aren't just scars, they're laboratories for studying extreme physics. For example, the galaxy NGC 5128, home to the famous radio source Centaurus A, reveals a gargantuan jet piercing through a dust lane, the aftermath of a merger that ignited its central black hole over 10 million years ago. To this day, that jet pumps out radio waves so powerful they're detectable from Earth with amateur equipment. The duration of these radio screams depends on the merger's violence and the black hole's appetites. Some galaxies, like the antennae galaxies, flare up for a mere 100 million years before their star-forming gas is exhausted or blown away by supernova. Others, particularly those with well-fed black holes, can remain radio loud for billions of years, their jets etching ever larger lobes into intergalactic space. The key factor is feedback. The same winds and shocks that amplify the radio emissions eventually disperse or heat the gas, starving the black hole and quieting the storm. It's a self-limiting cycle where the merger's violence sows the seeds of its own silence. Yet these collisions aren't just destructive, they're also creative. The heavy elements forged in merger-driven starbursts, carbon, oxygen, iron, get scattered into the cosmos, enriching future generations of stars and planets. Some simulations even suggest that without mergers, many galaxies, including our own Milky Way, might never have grown to their current sizes. The radio screams then are more than just noise. They're birth cries of new galactic structures, reminders that in the cosmos, creation and destruction are two sides of the same coin. What's humbling is realizing how much we're still piecing together. Every new radio observation of merging galaxies reveals surprises, unexpected magnetic field configurations, jets bending under gravitational forces, or even hints of pre-merger black holes dancing in ways that defy predictions. These systems are messy, unpredictable, and utterly fascinating. They force us to question not just how galaxies evolve, but how the universe orchestrates its grandest transformations. The next time you see a serene-looking galaxy in a telescope, remember, given the right cosmic nudge, it too could unleash a scream loud enough to echo across the universe. Quasars are the universe's ultimate screamers, cosmic beacons so bright they can outshine 1,000 galaxies combined, yet so mysterious they often hide in plain sight. These brilliant objects are actually active galactic nuclei in overdrive, powered by supermassive black holes feeding at breakneck speeds. What makes them truly extraordinary isn't just their raw power, but the stark contrast between how they appear across different wavelengths. From one angle, a quasar might look like an unremarkable smudge in visible light, its brilliance obscured by thick dust clouds. But flip the switch to radio frequencies, and the illusion shatters, its jets erupting across millions of light years, painting the cosmos with lobes of synchrotron radiation so vast they dwarf their host galaxies. The secret behind this duality lies in the quasar's anatomy. At its core, a black hole gorges on gas and stars, its accretion disk glowing white-hot with X-rays and ultraviolet light. But above and below this disk, magnetic fields channel some of that infalling material into jets, twin beams of plasma, accelerated to nearly light speed. These jets plow through intergalactic space like cosmic blowtorches, their collisions with surrounding gas creating shock waves that glow fiercely in radio waves. From head-on, we might see the quasar's dazzling optical light. But viewed edge-on, the dusty torus surrounding it blocks that visible glow, leaving only the radio jets visible, turning what seems like a dim galaxy into one of the loudest radio sources in the universe. Not all quasars are created equal, though. Some, known as radio-loud quasars, produce jets that dominate the radio spectrum, their lobes stretching far beyond their host galaxies. Others, called radio-quiet quasars, have weaker or absent jets, their energy radiating mostly in X-rays or visible light. Why this split? The answer might lie in a combination of factors: the black hole's spin, the availability of gas, and even the galaxy's environment. Faster spinning black holes can wind magnetic fields tighter, launching more powerful jets. Galaxies in dense clusters might have more gas to feed their black holes, while isolated quasars could starve between meals. Then there's the role of time. Quasars aren't eternal. They flicker on and off as their fuel supply waxes and wanes. A galaxy might spend millions of years as a radio-quiet quasar, then suddenly roar to life as a radio-loud monster when a fresh wave of gas spirals into its core. Some astronomers think these phases could be cyclical, with quasars alternating between states as their environment changes. It's a reminder that what we see, whether silence or screams, is just a snapshot in a dynamic, ever-evolving universe. What's truly staggering is the scale of their influence. Quasar jets can stretch for hundreds of thousands of light years, shaping not just their host galaxies but entire galaxy clusters. They heat intergalactic gas, suppress star formation, and even enrich the cosmos with heavy elements forged in their fiery hearts. In a sense, quasars are the universe's great regulators, their outbursts balancing cosmic growth and stagnation. And while their visible light might fade with time, their radio signatures linger, ghostly reminders of past fury written across the sky. The next time you gaze at a seemingly quiet patch of the night sky, remember, hidden in that darkness could be a quasar, its light dimmed by dust but its radio voice booming across the cosmos. These screamers teach us that brilliance isn't always what it seems sometimes. The universe's most dazzling secrets are written in wavelengths we're only learning to read. Radio galaxies are cosmic megaphones, colossal structures that dominate the radio universe while remaining eerily quiet in visible light. At their hearts, supermassive black holes don't just lurk. They unleash energy so immense it carves the sky into vast lobes of plasma, stretching distances that make entire galaxies seem like specks. These lobes, often spanning millions of light years, aren't fleeting fireworks, they're enduring monuments to some of the most violent processes in existence. But how does a black hole, famous for trapping light, become the engine behind such luminous radio behemoths? The answer lies in a delicate dance of gravity, magnetism, and raw cosmic power. Picture a black hole feeding on a galaxy's gas, its accretion disk glowing white-hot as material spirals inward. But not everything gets swallowed. Some particles, caught in the black hole's twisted magnetic fields, get slingshotted away at nearly light speed, forming jets that blast into intergalactic space. When these jets slam into the sparse gas between galaxies, they don't just stop. They plow through like cosmic bulldozers, piling up material into massive, radio-bright lobes. These structures aren't static, they're dynamic, evolving over millions of years as they expand and interact with their surroundings. What keeps these lobes glowing so long after the initial outburst? It's a combination of two key ingredients, a high-energy electrons and magnetic fields. As the jets pump particles into the lobes, those electrons spiral along magnetic field lines, emitting synchrotron radiation. The same process that lights up particle accelerators on Earth, but on a galactic scale. And because the lobes are so vast, the electrons take thousands of years to lose their energy, meaning the radio glow can persist long after the black hole's jets have flickered out. It's like a cosmic echo, a shout reverberating across the void long after the original voice has gone silent. The sheer size of these structures defies intuition. Take Centaurus A, a nearby radio galaxy whose lobes stretch over 1.5 million light-years, 15 times the diameter of our Milky Way. Or the galaxy Hercules A, whose lobes billow outward in intricate, bubble-like formations, sculpted by interactions with the surrounding intergalactic medium. These aren't just splashes in a pond, they're tsunamis, their energy reshaping entire swaths of the cosmos. But here's the twist, not all radio galaxies look the same. Some, like Cygnus A, display twin lobes perfectly aligned with their jets, textbook examples of symmetry. Others, like 3C75, show bent or distorted lobes, likely warped by collisions with other galaxies or the turbulent gas of galaxy clusters. These variations aren't just cosmetic, they're clues to the environments these galaxies inhabit, the density of the intergalactic medium, and even the history of their black hole's activity. The real puzzle is why some galaxies become radio giants while others remain quiet. The answer might lie in the black hole's spin. A faster rotation could mean stronger magnetic fields and more powerful jets. Or it could depend on the galaxy's fuel supply. A steady diet of gas might sustain longer, brighter outbursts. There's also the role of mergers, galactic collisions that funnel fresh material toward the black hole, reigniting dormant jets and sculpting new lobes. One thing's certain, radio galaxies force us to rethink what active means in the cosmos. A galaxy might look serene through an optical telescope, its stars twinkling quietly. But switch to radio, and the illusion shatters, revealing a history of violence, energy, and transformation written across the sky. These screaming giants remind us that the universe doesn't perform for human eyes alone. Its most spectacular dramas often play out in wavelengths we're only beginning to hear. The cosmic microwave background is often called the universe's baby picture, a faint glow left over from the Big Bang, stretching across the entire sky like a fossilized whisper from the dawn of time. But this ancient light isn't just a relic, it's also a cosmic detective, revealing secrets about the galaxies that came after it. As the CMB radiation travels through space, it doesn't pass through unscathed. Some of it encounters the superheated gas and magnetic fields surrounding radio-loud galaxies, and that's where the story gets fascinating. When these high-energy radio sources lie between us and the CMB, they leave subtle fingerprints, tiny distortions in the microwave light that astronomers can decode like cosmic breadcrumbs. One of the most telling distortions comes from the Sunyaev-Zeldovich effect, a mouthful of a name for something beautifully simple. Imagine the CMB photons traveling undisturbed for billions of years, suddenly hitting a wall of hot electrons in a galaxy cluster or the turbulent plasma around a radio galaxy. Those photons get a tiny energy boost like a ball bouncing off a moving truck, and that shift leaves a mark in the CMB data. It's as if the screaming galaxy cast a shadow, not in darkness, but in a distinct pattern of temperature fluctuations. By mapping these distortions, astronomers can pinpoint where these radio monsters lurk, even if they're hidden behind thick veils of dust that would block visible light entirely. But the CMB doesn't just help us find these galaxies, it helps us weigh them. The hotter and denser the gas around a radio galaxy, the stronger its imprint on the CMB. Some of the most massive galaxy clusters, brimming with radio-emitting plasma, warp the microwave background enough that astronomers can estimate their size and energy output without even seeing them directly. It's like feeling the heat of an invisible fire by how it warms the air around it. Then there's the time travel aspect. Because the CMB is so ancient, its interactions with later radio sources create a kind of cosmic double exposure, a snapshot of how galaxies have influenced their surroundings over billions of years. By comparing CMB distortions from different distances, astronomers can trace how radio galaxies have evolved, from the early universe's frenzied youth to the more sedate cosmic neighborhoods we see today. Some of the loudest screamers in the distant past have since gone quiet, their energy fading into the background hum of the universe. Others, like the nearby radio giant Cygnus A, remind us that the cosmos still has plenty of fireworks. What's truly remarkable is how these faint echoes of the Big Bang connect to the radio screams of today. The same processes that twist magnetic fields and accelerate particles in modern galaxies, black hole jets, supernova shocks, galactic winds, leave their marks on the CMB, linking the universe's birth to its ongoing transformation. It's a reminder that nothing in space exists in isolation. Even the oldest light carries stories of the chaos that came after, written in wavelengths we're only now learning to read. Neutron stars and pulsars may be tiny compared to galaxies, but their radio voices can be just as deafening. These stellar corpses, no larger than a city yet weighing more than our sun, pack so much energy into such a small space that they become cosmic lighthouses, beaming intense radio waves across the universe with precision timing. When a massive star collapses in a supernova, its core doesn't just fade away, it gets crushed into a neutron star where matter becomes so dense that a single teaspoon would weigh 1 billion tons on Earth. If that neutron star happens to spin rapidly with its magnetic poles misaligned, it transforms into a pulsar, sweeping the sky with radio beams like a celestial strobe light. What makes these objects so fascinating is how efficiently they convert raw power into radio emission. Unlike the chaotic, sprawling radio lobes of galaxies, pulsars emit tightly focused beams, often flashing with metronomic regularity. Some spin hundreds of times per second, their pulses arriving with clockwork precision. The Crab pulsar, for example, flickers 30 times every second, while millisecond pulsars whip around even faster, their stability rivaling atomic clocks. This isn't just energy, it's energy with rhythm, a signature so distinct that the first pulsar discovered, PSRB 1919+21, was initially nicknamed LGM-1, Little Green Men 1, because its pulses seemed unnaturally precise. Yet despite their intensity, pulsars operate on a completely different scale from galactic screamers. A supermassive black hole's jet might span millions of light years, but a pulsar's beam is minuscule by comparison, only a few kilometers wide. The difference lies in their engines. Galaxy-scale radio sources rely on the gravitational chaos of black holes and the slow churn of magnetic fields, while pulsars are powered by the absurd physics of neutron star matter, superconducting protons, superfluids swirling in their cores, and magnetic fields trillions of times stronger than Earth. It's the contrast between a forest fire and a laser beam, both bright, but one diffuses its energy across vast space, while the other concentrates it into a needle-thin shaft. This raises an intriguing question. If a pulsar's beam happened to point directly at Earth, could it outshine an entire radio galaxy? Surprisingly, yes, but only for that fleeting moment when its beam sweeps across us. The Vela pulsar, for instance, pumps out radio waves so intense that its pulses momentarily dominate the radio sky, despite being a fraction of a galaxy's size. But unlike the enduring roar of a radio galaxy, a pulsar's voice is transient, flickering in and out of detectability as it spins. What ties these tiny screamers to their galactic cousins is the sheer diversity of cosmic radio sources. From the faint whispers of cold gas clouds to the thunderous outbursts of black holes, the universe speaks in radio wavelengths with countless accents. Pulsars remind us that size isn't everything sometimes. The most powerful voices come from the smallest packages, and while they're not the focus of our silent galaxy mystery, they're a crucial piece of the puzzle, proving that radio waves can carry stories of both the unimaginably vast and the incomprehensibly dense. Fast radio bursts are the universe's most cryptic radio screams, blindingly bright flashes that last just milliseconds, yet pack more energy than our sun emits in days. These fleeting cosmic signals appear without warning, vanishing as quickly as they arrive, leaving astronomers scrambling to decode their origins. Some erupt just once, while others repeat sporadically, flickering like a malfunctioning cosmic beacon. What's baffling is their sheer intensity. Even the most powerful FRBs originate from sources so distant their light has traveled billions of years to reach us, meaning whatever's producing them must be unimaginably energetic. The leading suspects, extreme stellar remnants like Magnetar's neutron stars with magnetic fields so strong they could erase a credit card from halfway across the solar system. When these objects undergo starquakes or magnetic reconnection, they might unleash bursts of radio waves bright enough to pierce the cosmos. Other theories point to cataclysmic collisions, black holes shredding neutron stars, or two dense stellar corpses merging in a fiery embrace. But there's a twist. Some FRBs don't fit these scenarios. Their patterns are too erratic, their environments too calm, forcing astronomers to consider even wilder possibilities, like cosmic strings or primordial black holes. Now imagine a silent galaxy, one that appears dormant in visible light harboring similar explosive processes. Could sporadic FRB-like events be crackling through its depths, unnoticed because we aren't listening at the right moments? Radio telescopes typically scan the sky in broad sweeps, catching only the loudest or most persistent signals. A silent galaxy might host brief, brilliant radio screams too rare or faint for our current surveys to detect. After all, before FRBs were discovered, no one thought the universe could produce such intense, fleeting radio flashes. The parallels are striking. Both phenomena challenge our assumptions about what's normal in the radio sky. What makes FRBs especially tantalizing is their potential as cosmic probes. As these bursts travel across the universe, they pass through clouds of gas and magnetic fields, which subtly alter their signals. By analyzing these distortions, astronomers can map the invisible material between galaxies, the same stuff that might cloak silent galaxies in radio darkness. It's like using a flashlight in a foggy forest. The way the beam scatters reveals the fog's density. If silent galaxies emit similar bursts, even sporadically, they could become windows into their hidden structures. The deeper we look, the clearer it becomes. The radio universe thrives on extremes, from the enduring roar of active galaxies to the split-second shrieks of FRBs. These phenomena remind us that silence is often an illusion, a trick of limited perception. Every time we develop new ways to listen, the cosmos reveals another layer of its hidden symphony. Fast radio bursts may not solve the riddle of silent galaxies, but they prove one thing unequivocally: the universe is far louder, far stranger than we ever imagined. Hydrogen might seem like a quiet player in the cosmic drama. After all, it's just a single proton and electron, the simplest atom in existence. But in the radio universe, even the humblest element has a voice. Neutral hydrogen, floating undisturbed in the vast spaces between stars, emits a faint but unmistakable signal at a wavelength of 21 centimeters. This whisper, produced when the spin of an electron flips relative to its proton, is so subtle it was once thought impossible to detect. Yet today, it's one of astronomy's most powerful tools for unraveling the secrets of galaxies that otherwise appear silent. Mapping this 21-centimeter emission is like turning on a blacklight in a dark room. Suddenly, invisible structures glow into view. Take a seemingly dormant galaxy, its stars sparse and its center dark. Point a radio telescope at it, tuned to hydrogen's frequency, and the picture transforms. Vast reservoirs of gas, invisible to optical telescopes, reveal themselves in intricate detail. Some form sprawling, rotating disks, while others twist into tidal streams, leftovers from ancient collisions. These maps don't just show where the gas is, they show how it moves. By measuring subtle shifts in the hydrogen signal's wavelength, astronomers can trace the speed and direction of gas clouds, reconstructing the galaxy's hidden dynamics. The real magic lies in what these whispers tell us about galactic life cycles. In so-called red and dead galaxies, those that have stopped forming stars, hydrogen maps often expose a paradox: plenty of fuel but no fire. The gas is there, but something's preventing it from collapsing into new stars. Sometimes the culprit is a supermassive black hole, its past outbursts heating the gas so it can't cool. Other times, it's the aftermath of a galactic merger, where gravity's tug of war has left the gas too turbulent to settle. Without hydrogen's radio fingerprint, these galaxies would remain enigmas, their stagnation unexplained. But hydrogen's whispers aren't just about absence, they also hint at rebirth. In the outer fringes of some silent galaxies, astronomers find vast, lopsided gas clouds, their motion erratic. These could be the first signs of fresh fuel arriving, perhaps stripped from a smaller neighbor or siphoned from intergalactic space. Given time, this gas might spiral inward, reigniting star formation and pulling the galaxy back from the cosmic graveyard. It's a reminder that silence isn't always permanent. Sometimes it's just a pause. The 21-centimeter line also bridges the gap between the past and present. Because hydrogen is so abundant in the early universe, its emission lets astronomers peer back in time, comparing the gas-rich galaxies of billions of years ago with their quieter descendants today. The differences are striking. Ancient galaxies often have chaotic, bloated hydrogen reservoirs, while modern ones are leaner, their gas more orderly or outright missing. This evolution hints at a universal trend: galaxies start loud, with frantic star formation and messy gas dynamics, then grow quieter as they age, their fuel depleted or disrupted. What's astonishing is how much this faint whisper has reshaped our cosmic perspective. Without it, entire chapters of galactic history would stay hidden. We'd miss the stealthy mergers, the invisible fuel reserves, the quiet stirrings of revival. Hydrogen's radio signal proves that sometimes the universe's softest voices carry the deepest truth, if only we know how to listen. Galactic cannibalism is the universe's slowest, most brutal feast, a meal that takes billions of years to finish, yet leaves behind some of the loudest echoes in the cosmos. Picture a massive galaxy drifting through space, its gravity reaching out like invisible fingers, tugging at a smaller neighbor. Over eons, the smaller galaxy stretches, its stars and gas pulled into long, shimmering streams, tidal tails that glow faintly in visible light but scream in radio frequencies. This isn't just a merger, it's a cosmic feeding frenzy, where the larger galaxy's supermassive black hole gorges on fresh gas, reigniting dormant jets and flooding the void with radio waves. The key to this transformation lies in the chaos of the feast. As the victim galaxy's gas spirals inward, it doesn't fall smoothly. It collides, clumps, and shocks itself into a frenzy. Friction heats the gas to millions of degrees, turning it into a turbulent plasma that lights up in X-rays and radio. Some of this doomed material swirls into the black hole's accretion disk, revving it like an engine. Magnetic fields, twisted by the disk's rotation, launch newly energized jets, their particles racing outward until they slam into intergalactic gas, creating colossal radio-bright shockwaves. The galaxy, once silent, now roars not from starlight, but from the violence of its meal. But why does cannibalism trigger such extreme radio outbursts when other mergers stay quiet? The answer lies in the menu. Smaller galaxies are often gas-rich, their reservoirs untouched by the supernova and winds that drain larger systems. When this pristine fuel floods the central black hole, it's like throwing gasoline on a smoldering fire. Compare this to two massive galaxies merging. Their gas may already be depleted, their black holes starved past the point of a dramatic revival. It's the difference between a banquet and a snack. Only the former reignites the galactic engine with enough force to scream across the cosmos. The aftermath of these feasts is written in radio light. Telescopes like the Very Large Array have captured stunning images of cannibal galaxies with double nuclei, the lingering cores of two galaxies caught mid-meal, surrounded by sprawling radio lobes. These lobes, inflated by jets over millions of years, act like cosmic smoke rings, marking where the black hole's outbursts have plowed through space. Some, like the famous radio galaxy Centaurus A, even show dust lanes, the mangled remains of a devoured spiral galaxy stitched across their centers like scars. Yet cannibalism isn't just about destruction, it's also a catalyst for rebirth. The same gas that feeds the black hole can, paradoxically, seed new stars. As tidal forces compress gas clouds during the merger, some collapse into stellar nurseries, creating bursts of star formation that glow in infrared and radio. It's a cosmic cycle. Cannibalism fuels chaos, chaos births radio screams, and somewhere in the tumult, new stars and perhaps planets take shape, the most astonishing part. We're witnessing snapshots of a process that unfolds over cosmic timescales. A single merger might take 1 billion years from first approach to final digestion, with the radio outbursts flickering on and off like a neon sign with faulty wiring. That's why some silent galaxies aren't truly silent, they're just between meals. They're black holes fasting until the next galactic snack drifts too close. So the next time you see a galaxy glowing faintly in visible light but blazing in radio, remember, you might be looking at a cosmic predator, its screams echoing long after its feast has ended. The universe doesn't just build galaxies, it devours them, and in the process writes its most violent stories in wavelengths only radio ears can hear. Feedback mechanisms in galaxies operate like cosmic thermostats, fine-tuning the balance between creation and destruction, silence and scream. Picture a galaxy where stars form at a breakneck pace, their ultraviolet radiation and eventual supernova heating surrounding gas, pushing it outward in colossal winds. These winds act as a self-regulating force, dispersing the very material needed to make more stars. The result, a galaxy that gradually quiets in visible light as star formation dwindles, but erupts in radio frequencies as shockwaves from those same winds accelerate particles and amplify magnetic fields. This is feedback in action, where the energy of stellar birth stifles future births while broadcasting its aftermath across the radio spectrum. But black holes add another layer to this dance. When a supermassive black hole at a galaxy's core feasts on gas, it doesn't just consume, it retaliates. Jets and radiation blast outward, heating gas so intensely it can't cool and collapse into stars. In extreme cases, these outbursts can blow entire galaxies clean of their star-forming fuel, leaving behind a red and dead relic that's optically silent, but might still crackle with radio emissions from lingering shockwaves or dying jets. The galaxy's fate hinges on which feedback loop dominates, the stellar winds that gently press the off switch on star formation, or the black hole's tantrums that rip the switch clean off the wall. What tips the scales toward screaming? It often comes down to timing and environment. In dense galaxy clusters, where gas is plentiful and collisions frequent, black holes are more likely to binge on fuel, triggering violent outbursts that drown out stellar feedback. Isolated galaxies, by contrast, might settle into a quieter equilibrium, their star formation ebbing gradually without dramatic radio fanfare. Then there's the role of mergers, galactic pile-ups that funnel fresh gas toward black holes, reigniting their jets and tipping the balance from silence to scream. The radio-loud galaxy Messier 87, with its famous jet, is a prime example. Its supermassive black hole, fed by interactions with neighboring galaxies, has become a perpetual radio siren. Yet feedback isn't just an on-off switch. Some galaxies oscillate between states, their black holes flickering on and off as gas supply fluctuates. Others exhibit partial feedback, where star formation slows but doesn't stop, creating a hybrid, optically dim but not dark, radio bright but not deafening. The Milky Way's own supermassive black hole, Sagittarius A, offers a glimpse of this middling state. Occasionally snacking on passing gas clouds, it emits faint radio whispers rather than roars, its feedback too weak to quench star formation entirely but enough to stir the galactic pot. The real marvel is how these processes scale across cosmic time. In the early universe, galaxies were gas-rich and chaotic, their feedback loops more like frenzied shouting matches. Today, many have settled into quieter rhythms, their star formation exhausted or stifled by past outbursts. But every so often, we catch a galaxy in transition like a silent giant waking from slumber, its radio scream a fleeting echo of the forces that shape galactic life. Feedback doesn't just explain why some galaxies scream and others stay silent. It reveals the universe as a dynamic, self-regulating system, where even the faintest whispers carry the weight of cosmic history. The cosmic web is the universe's hidden nervous system, a sprawling, intricate network of dark matter and gas filaments that threads through the cosmos, connecting galaxies like beads on an invisible string. In visible light, this web is nearly impossible to see, its delicate strands lost in the blackness between stars, but switch to radio frequencies and the silence shatters. The same gas that forms the web's skeleton, thin as it is, can glow faintly in radio waves, especially where it's been shock-heated by collapsing galaxy clusters or stirred by the gravitational pull of passing dark matter. These emissions trace the web's architecture, revealing how even seemingly isolated galaxies are cradled by this vast, whispering scaffold. What's astonishing is how this web doesn't just connect galaxies, it feeds them. Picture a silent galaxy drifting through a dense filament of the cosmic web. Over millions of years, gravity funnels gas along these filaments like water through a pipeline, delivering fresh fuel to the galaxy's core. If that galaxy hosts a supermassive black hole, the influx of gas can awaken it from dormancy, igniting jets and radio lobes that transform the galaxy from a quiet bystander to a screaming participant in the cosmic chorus. This isn't just theoretical. Radio telescopes have spotted galaxies positioned at the intersections of web filaments, their outbursts perfectly aligned with the invisible rivers of matter flowing into them. But the web's influence goes deeper. When galaxies collide a common fate in the dense nodes of the cosmic web, the resulting chaos can compress gas, trigger starbursts, and jolt black holes into action. These collisions don't just light up the galaxies involved, they send shockwaves rippling along the web's filaments, energizing gas far beyond the merger site. In radio observations, these shock fronts appear as diffuse, glowing bridges between galaxies, evidence of the web's role as both a highway for matter and a conductor for energy. Then there's the dark matter's silent hand. While it doesn't emit radio waves itself, its gravitational pull shapes the web's structure, dictating where gas accumulates and galaxies form. The densest knots of dark matter become the nurseries for galaxy clusters, where radio-loud behemoths like Cygnus dominate. In quieter regions where filaments are sparse, galaxies may remain gas-starved and silent, their black holes fasting in the dark. The cosmic web, then, isn't just a backdrop, it's a dynamic stage manager, scripting where and when galaxies scream. The real revelation here is scale. The web's filaments stretch for hundreds of millions of light-years, meaning a single galaxy's radio outburst might be influenced by events halfway across the universe. A disturbance in one node, a merger, a black hole's awakening, can send ripples along the filaments, affecting galaxies far downstream. It's a reminder that no galaxy is truly isolated. Each is a single note in a symphony orchestrated by the web's invisible hand. So when we point our radio telescopes at a seemingly silent galaxy, we're not just studying an island in the void. We're seeing a node in a living network, where dark matter's gravity and the web's rivers of gas conspire to shape destinies. The screams we detect aren't random, they're the echoes of a grand, billion-year dance, choreographed by the universe's largest and most elusive structure. And every time we map another strand of this web, we're decoding the hidden language of cosmic connection. The square kilometer array isn't just another telescope, it's a revolution in how we listen to the cosmos. Sprawling across deserts in South Africa and Western Australia, this colossal network of antennas will act as a single dish with a collecting area of, you guessed it, 1 square kilometer. That's enough sensitivity to detect an airport radar on a planet tens of light years away, or pick up the faintest radio whispers from galaxies so distant their light has traveled billions of years to reach us. Imagine turning up the volume on the universe's quietest corners, catching murmurs from galaxies that today's telescopes dismiss as static. The SKA won't just hear cosmic screams, it'll eavesdrop on whispers we didn't even know existed. One of its prime targets, the era of cosmic dawn, when the first galaxies flickered to life. Current telescopes glimpse these pioneers as fuzzy radio blobs, but the SKA will dissect them in stunning detail. We might catch supermassive black holes in their infancy, their jets barely strong enough to pierce the primordial gas around them, or spot the turbulent birth of magnetic fields, watching as they weave through young galaxies like invisible threads. These observations could solve a long-standing puzzle: why some early galaxies, despite their frenzied star formation, appear eerily quiet in radio while others scream. The answer might lie in the delicate balance between magnetic field strength and gas density, a dance the SKA could witness in real time across cosmic history. Then there's the mystery of intermittent screamers, galaxies that flicker between silence and radio fury. Today, we catch these transitions by luck, like stumbling upon a thunderclap in a silent forest. The SKA's relentless gaze will monitor millions of galaxies continuously, spotting flares as they happen. Imagine watching a dormant black hole suddenly awaken, its jets sputtering to life as a passing star or gas cloud strays too close. Or tracing how mergers between galaxies, slow-motion crashes lasting hundreds of millions of years, trigger radio outbursts at precise moments in the collision. This isn't just about cataloging events, it's about decoding the triggers that turn silence into screams. But the real game changer is the SKA's ability to map hydrogen in unprecedented detail. Remember the 21-centimeter line, that faint whisper of neutral hydrogen? The SKA will detect it from galaxies so faint they're practically ghosts, revealing their hidden fuel reserves. Some of these might be stealth screamers, galaxies with ample gas but no star formation, their silence defying conventional wisdom. Are there black holes heating the gas invisibly? Is some unknown force suppressing star birth? The SKA's hydrogen maps could expose processes we've never even considered, rewriting the rules of galactic evolution. And let's not forget the unexpected. Every leap in observational power has unveiled phenomena nobody predicted: pulsars, quasars, fast radio bursts. The SKA, with its staggering sensitivity, might discover entirely new classes of radio sources. Perhaps galaxies that scream in bursts too rapid for current telescopes to catch, or ones whose radio emissions pulse in cryptic patterns. There could even be dark radio galaxies, systems so devoid of stars that their radio jets, powered by pure gas accretion, are their only visible feature. The universe has a habit of confounding us just when we think we've got it figured out, and the SKA is our best shot at hearing its next surprise. What makes this future so thrilling isn't just the technology, it's the questions we haven't thought to ask yet. The SKA won't just provide answers, it'll redefine what we're curious about. Every faint scream it detects from a silent galaxy will carry echoes of the forces that shape the cosmos, from the smallest magnetic field twist to the largest gravitational tug. And as we listen, we're not just observers, we're time travelers tuning into a broadcast that's been streaming for billions of years, finally ready to hear the full story. Simulations are the universe's digital echo chambers, supercomputer-powered laboratories where galaxies scream in ones and zeros, revealing secrets no telescope could capture alone. Picture a virtual galaxy, its gas, stars, and black hole meticulously coded into existence, then set in motion under the unrelenting laws of physics. Within this digital cosmos, astronomers can tweak gravity's pull, amplify magnetic fields, or starve a black hole of fuel, watching in real time how these changes ripple into radio emissions. It's like rewinding a cosmic film strip, playing it forward again and again until the patterns snap into focus, one of the most startling revelations from these simulations. The delicate balance between chaos and control. Take a supermassive black hole's jet, a structure so precise it can drill through galaxies for millions of light years. Simulations show these jets aren't just brute force explosions. They're sculpted by magnetic fields wound tighter than a watch spring, channeling energy with eerie precision. When researchers digitally turned off magnetism in models, jets fizzled into turbulent clouds, their radio glow scattering into noise. This explained why some galaxies, despite having active black holes, remain radio quiet. Without the right magnetic scaffolding, their screams dissolve into whispers. But simulations don't just replicate reality, they predict it. Before telescopes spotted them, models hinted that black hole jets could precess, wobbling like spinning tops as they interact with misaligned gas disks. When the Event Horizon Telescope later observed this very behavior in galaxy M87, it was a triumph of virtual astronomy. Similarly, simulations of colliding galaxies revealed that mergers don't just ignite radio outbursts, they can twist jets into corkscrews, leaving radio bright spirals in their wake. These digital discoveries became roadmaps for observers, telling them where and how to look for real-world counterparts. The limitations, though, are as telling as the successes. Simulating even a single galaxy requires trade-offs. Some models prioritize gas dynamics but simplify magnetism. Others track star formation in detail but approximate black hole physics. When simulations clash with observations like predicting radio lobes that are too symmetrical or jets that fade too quickly, it's a sign that key physics is missing. One persistent puzzle: how black holes couple with their host galaxies. Models struggle to replicate why some galaxies flicker between radio loud and quiet states, suggesting hidden variables like chaotic gas clouds or rare stellar collisions might be pulling the strings. What's emerging is a new kind of cosmic dialogue. Telescopes spot anomalies, simulations decode them, and refined models guide fresh observations. For instance, when radio arrays detected orphan radio lobes, structures unconnected to visible jets, simulations traced them to ancient black hole outbursts, their jets long vanished but their shockwaves still glowing. Other models recreated the bizarre, X-shaped radio galaxies, revealing them as relics of black holes that flipped spin axes during mergers, their jets abruptly changing direction mid-eruption. The ultimate test, simulating a galaxy from first principles, starting with the primordial gas of the early universe and letting gravity, thermodynamics, and magnetism sculpt it over billions of years. The most ambitious attempts, like the Fire Project, now produce virtual galaxies with realistic radio signatures, their star formation rates and black hole activity aligning eerily with real surveys. Yet even these staggeringly complex models can't yet capture the full tapestry of cosmic feedback, where stellar winds, supernova, and black hole jets intertwine across scales from light years to megaparsecs. What's clear is that simulations aren't just tools, they're telescopes for the mind, letting us experiment with universes where the rules can be bent, broken, or reinvented. Every mismatch between model and observation is a clue, every virtual success a stepping stone. As supercomputers grow more powerful and algorithms more refined, these digital galaxies will inch closer to reality, whispering or screaming the secrets of their silent counterparts. Citizen science has turned cosmic discovery into a team sport, where anyone with curiosity and an internet connection can help decode the universe's hidden screams. Projects like Radio Galaxy Zoo harness the power of collective observation, inviting the public to sift through radio telescope data and match mysterious emissions with their optical counterparts. Imagine scrolling through images of distant galaxies, some serene in visible light but crackling with radio energy, and flagging oddities that might stump even seasoned astronomers. This isn't busy work, it's frontline research. When thousands of eyes scour the same data, patterns emerge that algorithms might miss: a faint jet curving oddly, a lobe asymmetrical enough to hint at a past collision, or a radio source with no visible galaxy at all. These anomalies often lead to breakthroughs, like the discovery of hybrid galaxies that defy classification or orphaned radio lobes with no clear parent black hole. The beauty of these projects lies in their accessibility. No PhD or fancy equipment is needed, just a willingness to learn and a dash of patience. Tutorials guide newcomers through the basics: how to distinguish a black hole's jet from a starburst's radio glow, or why a galaxy might appear silent in one wavelength but scream in another. Over time, volunteers develop an intuitive grasp of cosmic anatomy, spotting quirks that automated systems overlook. One standout example: a citizen scientist in Radio Galaxy Zoo noticed a peculiar alignment of radio sources that turned out to be a rare double-double galaxy, a system with two pairs of radio lobes, evidence of a black hole erupting in multiple outbursts over eons. Professional astronomers had missed it, the human eye caught it, but the impact goes beyond individual discoveries. By crowdsourcing data analysis, these projects tackle a modern astronomy paradox. Telescopes like the Square Kilometre Array will soon flood researchers with more data than any team could process alone. Citizen scientists act as a distributed supercomputer, filtering the signal from the noise. Their classifications train machine learning algorithms, helping AI recognize subtle cosmic signatures faster. It's a symbiotic loop. Humans teach machines, machines amplify human efforts, and together they map the universe's radio whispers at unprecedented scale. What's often overlooked is how these projects democratize wonder. A teacher in Nairobi, a retiree in Oslo, and a student in Mumbai can all contribute to papers published in top journals, their names listed alongside professional astronomers. For many, it's not just about the science, it's about connection. Online forums buzz with volunteers debating oddball galaxies, sharing screen grabs of their favorite finds, or celebrating when a target they flagged gets follow-up observation time on a major telescope. The thrill of participation is contagious. One volunteer described the experience as time traveling through data, knowing each click might reveal something no one has seen before. The next frontier, real-time citizen science. Imagine getting a phone alert when a distant galaxy's radio flux spikes unexpectedly, prompting you to log in and classify the outburst before it fades. Or collaborating with professionals during live telescope observations, voting on which mysterious source deserves deeper scrutiny. Tools like these are already in development, blurring the line between observer and participant. In an era where the universe's radio screams grow louder with every technological leap, the human element remains irreplaceable, because sometimes the key to unlocking cosmic mysteries isn't just more data, but more eyes, more curiosity, and more people willing to listen. Despite the leaps we've made in understanding radio-loud galaxies, the cosmos still guards its secrets fiercely. Why does one galaxy, seemingly identical to its neighbor in size and shape, erupt in radio fury while the other remains hushed? The differences can't always be explained by black hole size or gas reserves alone. There's a missing variable, a hidden switch that flips silence into scream. Some theories point to magnetic field geometry, where the precise alignment of a galaxy's invisible magnetic scaffolding determines whether particles accelerate efficiently or scatter uselessly into space. Others suggest it's about timing, a black hole's spin axis wobbling like a slowing top, its jets flickering on and off over cosmic epochs. Then there's the wild card of dark matter, whose gravitational nudges might subtly alter gas flows, tipping the scales toward outburst or quietude. The transitions between these states are even more baffling. Take NGC 5128, home to the colossal radio source Centaurus A. Observations suggest it wasn't always a screamer. Its current outburst likely began around 10 million years ago, triggered by a merger that dumped fresh gas onto its central black hole. But what about galaxies like Messier 87, whose jets have blazed steadily for far longer? The difference might lie in the fuel delivery system. A sudden, chaotic influx of material like a shredded star or a gas cloud plunging haphazardly into the abyss could ignite a short-lived radio episode. In contrast, a smooth, steady drip of gas from a stable accretion disk might sustain quieter, more enduring activity. It's the cosmic equivalent of comparing a bonfire to a candle. Both burn, but one roars while the other flickers. Then there are the outliers, galaxies that defy all expectations. Consider the so-called red geysers, aging systems with little star formation yet bizarrely strong radio emissions. Their black holes aren't actively feasting and their gas reservoirs are sparse. So what's powering their screams? One provocative idea involves cosmic weather, slow, persistent winds from earlier black hole outbursts that linger like atmospheric pressure systems, re-accelerating particles long after the initial blast. Another theory blames hidden pulsars, their collective radio buzz masquerading as a galaxy-wide roar. These oddballs remind us that the universe rarely follows tidy rules. How close are we to cracking these puzzles? The answer lies somewhere between frustration and exhilaration. New telescopes like the Square Kilometre Array will map hydrogen in silent galaxies with unprecedented detail, potentially revealing hidden reservoirs or shock fronts. Gravitational wave detectors might catch the ripples from black hole mergers, offering clues about how these collisions reignite radioactivity. And advanced simulations are finally incorporating the messy, small-scale physics like plasma turbulence and magnetic reconnection that could tip a galaxy from quiet to loud. Yet for every mystery solved, two more emerge. Perhaps that's the real lesson. The cosmos isn't just a puzzle to be solved, but a conversation that never ends. Each answer peels back a layer, only to expose deeper questions, and that's what makes the hunt so thrilling. The screams of silent galaxies are more than just cosmic oddities. They're a profound reminder that the universe operates in wavelengths far beyond human perception. What looks like emptiness to our eyes crackles with energy when we listen through radio telescopes, revealing black holes feasting, stars being born in chaos, and magnetic fields sculpting the void like invisible hands. This hidden symphony forces us to confront a humbling truth. We've been decoding the cosmos with only half the alphabet, missing entire chapters written in radio light. Take something as seemingly simple as darkness. Invisible to us, it might be thrumming with the aftermath of a black hole's last meal, its jets carving through space long after the visible fireworks have faded. Or consider a faint smudge in a telescope's eyepiece. What appears to be a relic could actually be a powerhouse. its radio roar betraying star formation so intense it defies logic. These contradictions aren't flaws in our understanding. They're signposts pointing to deeper layers of physics we're only beginning to grasp. Radio astronomy has been our guide through this unseen landscape, transforming static into stories. Every advance in technology, from the first clunky arrays to the sprawling square-kilometer array, acts like turning up the volume on a cosmic broadcast. Suddenly, magnetic fields reveal their intricate webbing, particle accelerators the size of galaxies snap into focus, and even dark matter's gravitational whispers become slightly clearer. It's as if we've been handed a pair of supernatural headphones, allowing us to eavesdrop on the universe's most private conversations. What's next? The frontier is wide open. With tools like the SKA, we might catch galaxies in the act of switching states quiet one millennium, screaming the next, or discover entirely new classes of objects that blur the line between star and black hole. There could be radio phenomena we haven't even imagined yet, waiting in the noise between frequencies. And let's not forget the potential for citizen scientists to spot anomalies that algorithms miss, turning amateur curiosity into professional breakthroughs. But beyond the science, there's something deeply poetic about silent galaxies that scream. They remind us that wonder isn't reserved for the obvious, the glittering stars, the swirling nebulae. Sometimes the most extraordinary secrets lurk in the quietest corners, revealed only to those who think to listen. So the next time you gaze at the night sky, remember, the darkness isn't empty. It's vibrating with stories we're just learning to hear. What cosmic mystery grabs your imagination? Drop your thoughts below, and don't forget to subscribe for more journeys into the unseen universe. The next revelation might be just one wavelength away.